All right, so we will move on to start talking about some things related to the interactions of electromagnetic radiation with matter. So we're transitioning into something new now, and as I mentioned when I got started with this last time, we've talked about the structure of the atom, but we have not talked really about how the electrons arrange themselves in an atom, which is really the most important aspect of atomic structure when it comes to chemistry. We've talked about the nucleus, but we're going to primarily talk about the electrons as we go forward. And at the time when scientists didn't have a clear picture for how electrons arrange themselves in atoms, and one thing they started doing was experimenting with the interaction of light or other forms of electromagnetic radiation with matter, and that led to some very new and very important ideas in the field. So we started last time by talking about the properties of a wave, and we drew some. I had some pictures of waves up here, and we talked about three main parameters that you can use to define waves. We had wavelength, frequency, and amplitude. Now we're not really going to talk about amplitude anymore, but we should be aware that it does exist. But we're going to focus on our wavelength and frequency. These are the two most important properties of a wave as we go forward in this course. All right, so we saw last time, just by looking at pictures of waves and qualitatively defining the wavelength and the frequency, that there is an inverse relationship between the two, which means as the wavelength gets larger, the frequency gets smaller, and vice versa. If the frequency gets smaller, the wavelength gets larger. So you have an inverse relationship, which you can write as this. So lambda, which is wavelength, is proportional to 1 over the frequency. So that's what it means to be inversely related, and this little curly sign means proportional to. It doesn't mean that's an equality. It's not that it's equal to 1 over the frequency, but they are related in that sense. And a common trick in mathematics, which we'll use when introducing a number of the equations that we're going to be dealing with in this course, is if you have a proportionality like this and you want to turn it into an equation, you just have to add a constant to one side of the equation. So we can write that lambda is equal to some constant c over the frequency, and now it's an actual equality. And this it can often be rewritten as lambda times the frequency, nu times lambda equals c in either order, doesn't matter of course. And this c that we have in this equation is a very special constant, which is the speed of light. So the wavelength and frequency are related by the speed of light. This is on the periodic table and list of constants that we provide for you in this course, so you don't have to memorize this, but it's 3 times 10 to the 8th meters per second. That's the value for a vacuum. We're not going to worry about the effect of other medium on the speed of light, but in a vacuum it's 3 times 10 to the 8th meters per second. It's very similar to that in air, as it turns out, so we don't need to worry about those small differences. Now keep in mind that this is meters per second, you have this relationship. The wavelength, though, lambda, is often given to you in nanometers. So we can now classify different types of electromagnetic radiation based on either their wavelength or frequency. And again, this scale here shows as the wavelength increases, the frequency decreases. As the frequency increases, the wavelength decreases. And so by dividing up by different categories using the wavelength and frequency, we can have this scale here. So what you have is, and we should memorize the order of these. There's only, 7 of them, so it's not too bad. Visible light is more or less right in the middle. That's the electromagnetic radiation that we can see. And that's going to span a range of wavelengths that's a little bit small. This is 400 nanometers to 750 nanometers. Nanometers is the most common unit for wavelength that we'll see, especially for things in the visible range. So 1 nanometer is 10 to the minus 9 meters. So visible light has a very, very small wavelength, relatively speaking, so we don't use meters to define it, but more commonly nanometers. So from 400 to 750, a relatively small range, but sort of right close to the middle of the total scale here, we have our visible light, which has the familiar order of red, orange, yellow, green, blue, violet, Roy G. Biv, as you've all heard about before, where the red is on the side that has the higher wavelength or the lower frequency, and the violet is on the side that has the lower wavelength or the higher frequency. And then below that we have, and then on either side of the visible light we have other categories of the electromagnetic radiation. So if we go just to higher frequency from visible or just below in wavelength, we call that ultraviolet. So that's going to be the one that's higher in frequency or smaller in wavelength than visible. And then we have X-ray and gamma ray going in this direction. And then going in the other direction, the frequency of electromagnetic radiation that's just below the visible range we call infrared. That means below red. Ultraviolet means above violet, so that's where those names come from. And then beyond infrared, we have microwave and radio waves. And so we've probably heard of most of these in several contexts, and they're just electromagnetic radiation, same waveform, but they have different frequencies and different wavelengths. And you definitely, for some of the homework and exam problems, you're going to want to know the order that these fall in terms of both wavelength and frequency. So just those 7, at least know what order they come in. You don't have to know the specific numbers that divide them up, and those are a little bit arbitrary anyway, but know at least the order that they come in, please. Okay. So that's how we categorize waves, and that's the relationship between the frequency and the wavelength. So what that means now is if we have wavelength or frequency, we can find the other parameter by just using that simple equation. So if we have orange light, which has 600 nanometer wavelength, then what's going to be the frequency of this orange light? Okay? So we have this simple relationship. Frequency times wavelength is equal to C. And we want to find out what the frequency is, so we solve for that, and we get C over lambda. All right, so C is a constant. It's going to be always given to you, 3.00 times 10 to the 8th meters per second, and then we're going to divide that by the wavelength. Now, the part where very many people mess up when they're doing these problems, the math is not difficult, the equations are not difficult, but we have to always be mindful of units. And I know there are a non-trivial subset of the population in this room that will refuse to write units when they're doing problems, and I encourage you to abandon that practice and actually write them out and be very mindful of them, because what the common mistake that people make is this speed of light is given to us in meters per second, but then we have the wavelength, which is often given to us in some other unit, in this case nanometers. So we can't just slap this 600 down here and call it a day. We have to convert this to the correct units, which is going to be meters if we're using the standard speed of light in meters per second. So don't forget to convert the wavelength when necessary. So if we want the wavelength in meters for this problem, we take that 600 nanometers and we do a conversion where we have 1 meter has 10 to the 9th nanometers, or you could invert it and say 10 to the minus 9 meters per nanometer, either way. But we cancel out nanometers, and that converts this into meters, which comes out to 6.000 for being careful with significant digits, times 10 to the minus 7 meters. So that's the value that we need to put into the denominator of this expression up here. We can't just use the given value of 600, because that's the wrong unit. Okay, 6.000 times 10 to the minus 7 meters, and now the meters cancel out. The units that we don't want cancel out, and we do the division, and we get 5.000 times 10 to the 14th. Now the unit, as we talked about for frequency, is either inverse seconds, seconds to the minus 1, or often referred to as hertz. And then sometimes we didn't specify it in this problem, but again, this is a pretty large number, 5 times 10 to the 14th. So very often for frequencies, we're going to put a prefix in there that makes it a little bit simpler. So this would simplify to 500 terahertz. You've probably heard of the unit terahertz in the context of computer speeds and things of that sort. So we can rewrite that as 500 terahertz. Of course, I didn't specify units here, but in Blackboard we will. So be familiar with the prefixes. So I didn't mention this before, but I have mentioned that you're responsible for that review chapter. And a very important part of that review chapter are the unit prefixes. So I'll remind you of that here. There's a Did I give that to you here? Yes, I did. Okay, so table R2 if you have the textbook, and for those of you that don't have the textbook, I reproduced it here. So these are the prefixes we want to be aware of, and it will come up a lot in this part of the course when we're talking about wavelength and frequency, because as I mentioned, wavelength is often nanometers or other units, not usually in meters, and frequency is often in something like gigahertz or terahertz or something much larger than a hertz. Okay? So be familiar with these prefixes because we will use them, and we do expect you to know these, although I won't go through them in any gory detail. All right, so that's the relationship between wavelength and frequency. Now, the other part of electromagnetic radiation we need to talk about, and really what's kind of the beginning of what we call the quantum theory, is the energy of electromagnetic radiation. And so, and really the energy of electrons and atoms as well, which are two very related concepts. So now that we know a little bit about the properties of electromagnetic radiation, let's talk about some of the key observations and key experiments that people did involving light and matter. And so one of these is called black body radiation, and if any of you have an electric stove, you've already seen this in your real life. So if you heat up certain metals primarily to very high temperatures, they glow. Okay, we've seen that in stoves. This is some sort of heating iron of some sort. I don't know what that is, but it looks cool, so I put it on here. But if you take a metal and heat it up to a really high temperature, it glows, and the color that it glows, of course, depends on how high you heat it up to. So that's the concept. So there are some observations about black body radiation that led scientists to believe that some of their ideas were wrong. So a solid heated to very high temperature and we're talking around 1,000 Kelvin here, or higher, emits visible light and probably some infrared as well, but that's what we see is the visible light. So that's what we observed. And this idea by itself was not too terribly upsetting, but then some scientists did some very careful experiments where they measured what is the frequency and wavelengths of the light that are coming off of these heated objects. So the problem that arose is that people again were stuck in the world of classical physics, just the simple Newtonian physics that had been around for hundreds of years. And using classical physics, you would predict that matter can absorb or emit any quantity of energy. So in other words, the energy of electrons in matter, electrons in atoms, is continuous. There is no quantization of any sort. It's just continuous energy. That's what people thought at the time. But when they did some experiments with black body radiation, it didn't really fit the theory. So this classical theory fails to explain the wavelength intensity relationship of black body radiation. Alright, so we're not going to worry about the details of this too much, but basically classical physics led to the prediction that there would be a lot of ultraviolet light coming off of these black body radiators, but in reality there's almost no ultraviolet light, and there's a peak sort of in the middle of the visible range, and then there's less intensity in the ultraviolet, less intensity in infrared. So they couldn't explain why that was using classical theory. So the math behind the solution and the rationale behind the solution is pretty complex, so I'll just go ahead and give you the solution. And this explanation was formulated by a guy named Max Planck, a very famous scientist, German as you might imagine. And his idea was that energy is quantized so that matter cannot just absorb or emit any single quantity of energy. And it's quantized in whole number multiples of a constant h times the frequency. Alright, so in other words, when this solid gives off light and its energy level is changing as it gives off the light, the change in energy is going to be some multiple n times h times the frequency, where h is constant 6.626 times 10 to the minus 34 joules times second, which is now named after Planck's constant. Or I guess if you use I'm from the Midwest, so if you use the Midwest pronunciation, it's Planck's constant, but Planck is probably the more proper pronunciation. And n is some integer value. So in other words, you can't just have any quantity of energy given off by a black body radiator. It has to come off in little packets that have a value of h times the frequency, and then some multiple of h times the frequency is the total energy. So as we'll talk about this and more as we go on, but essentially this is in some sense almost like an atomic analogy for electromagnetic radiation. The electromagnetic radiation comes off in little tiny individual packets of energy, not as a continuous spectrum. And just like with matter, it exists as little tiny particles called atoms, and not just as a continuous entity. So this was the idea that Planck came up with to explain black body radiation, which is that the energy of electrons is quantized and cannot just have any simple value. So that was kind of the start of it. And then the one that I think clarifies things even more, specifically related to the quantization of light energy, is called the photoelectric effect. So this was another experiment that people started doing and couldn't explain using simple physics. And so the person who came up with this is someone you've probably heard of, Albert Einstein. And this was essentially gave us further confirmation that energy is quantized, specifically in electromagnetic radiation. So the concept here, what we're doing is we're taking light of different wavelengths or different frequencies, and we're shining it onto a metal surface. And when you do that, you sometimes see electrons ejected. So you shine light on a metal surface, and it ejects electrons from the surface. Alright, so again, this was a common observation, but the problem is when people started looking at this in more detail, some things didn't quite fit what they would have expected. So the first thing is that the light must have a minimum frequency, what we call the threshold frequency, in order to see any electrons coming off. So we call this the threshold frequency. Below this value, so if the frequency is less than the threshold frequency, no electrons are ejected, regardless of the intensity of the light that you use. Alright, so the idea at the time was, and if we look at this picture here in more detail, it sort of shows it in an arbitrary sense. So this is, the writing is kind of small, but this is a potassium surface. And what they observed is if you have 700 nanometer light, which is red, in the part of the visible spectrum, they shine 700 nanometer light on the surface and nothing happened. And the prevailing idea at the time was, okay, just dial it up, turn up the intensity, hit it with a bigger hammer. But no matter how intense the light was, if it had this same wavelength and frequency of 700 nanometers, nothing happened. It didn't matter how much they dialed up the intensity. So the solution that Einstein came up with was the idea that light energy is also quantized. So we talked about last time, black body radiation sort of showed us that the energy of electrons in matter is quantized, has certain available energy levels that it can exist at. And this one also then said that light behaves the same way. So instead of being purely wave-like in nature, light consists of little particles. This is a analogy to matter, and we call those photons. And the energy of a photon, this is the equation that Planck came up with, and it applies to light energy as well, is equal to h times the frequency, which we can rewrite as h times c divided by lambda. All right, so this is just combining those two equations. H times the frequency, and then frequency is c divided by lambda, so you can write it in two different ways. So this is the energy of an individual photon. So essentially what happens is that light is made up of a collection of what we call photons. Each has a defined energy that depends on the frequency. And in the case of red light, the photon energy is not high enough to eject an electron from the surface. If you make the light more intense, you give it more photons, but each of those individual photons still has the same energy and nothing happens. Now, in other cases, if you go to green light, 550 nanometers, this one would eject an electron, and the speed would be observed as 2 times 10 to the 5th. If you go to higher energy light and you eject an electron, the speed is even higher. So once you get past the threshold frequency, you do see electrons ejected from the surface, but if you increase the intensity of the light, you don't see the electrons coming off faster, you just see more electrons coming off. So essentially each individual photon can eject one electron, and the energy of the electron that comes off depends on the energy of the single photon that hits it. So that's the concept of light being comprised of little particles of energy called photons. So this equation gives us the kinetic energy of the electron. Now, I don't think we're going to use this in any of the homework assignments or exams, but the concept is further driven home here. So the kinetic energy of the electron as it comes off the surface is 1/2 mv squared, where m is the mass of the electron and v is its velocity as it comes off. And that's equal to h nu, where this is the frequency of the photon that hits the surface, minus h times nu 0, where this is that threshold frequency. All right, so if our frequency of our light is above the threshold frequency, we have some extra energy, and that energy gets converted into kinetic energy for the electrons. But as I said, you can add higher intensity light, you can add more photons, you'll get more electrons coming off the surface, but they will always have the same speed as long as the frequency of the light is kept the same. So this idea brought home the point that light energy also is quantized. So you don't have continuous energy in a beam of light. You have little packets of energy called photons. Now, each individual photon has an extremely tiny amount of energy associated with it. So this is one of the reasons why people didn't realize it at the time. Keep in mind, Planck's constant H is on the order of 10 to the minus 34 joule. That's a tiny, tiny amount of energy, even if the frequency is relatively high. So each little packet of energy is tiny, but a beam of light then is a collection of those photons, and the total energy then would be the sum of all of those. So this was one idea that also came about to reveal the quantization of light. Now, another thing we need to talk about is, as we're getting into, is what's called wave-particle duality. So when you learn about light in classical physics, and when I first introduced it to you in this course, I introduced the idea that light was a wave. But now we're seeing that light also has particle properties. It has little packets called photons, and they can interact with electrons and eject them from a surface. So in some sense, it behaves like a particle as well. And so this idea here is called the wave-particle duality. And the person who really came up with the relationship for this was de Broglie. So de Broglie was French, and he was very young when he came up with this. I think he was a PhD student, and he has a PhD thesis that's about 2 pages, which is essentially this idea. And of course, it's one of the most important ideas in modern physics and chemistry, so he gets a pass for only having a 2-page thesis, whereas the average PhD thesis is about 200 pages. So that was a very important idea, and I don't think he didn't really do any experiments on this. It was just sort of a thought experiment. So keep in mind that the energy of a photon is hc over lambda, and the idea that de Broglie came up with is that there's this duality between waves and particles, that they're really not two separate things, that everything is both a wave and a particle, which is kind of a far-out thought, but it does in fact prove to be true in certain in all situations, but it's very noticeable in some situations. So Einstein came up with this equation that E is equal to mc squared. So using this equation, we can, and this is really more applied to nuclear physics, where this is the binding energy of a nucleus. But what de Broglie did was he rearranged this equation and he found the effective mass of a photon. So if a photon has particle-like properties, if light behaves as both a particle and a wave, we should be able to define a mass for it. So the effective mass of a photon is E over c squared, and we know that the energy for a photon is hc over lambda. So we can rewrite this as hc divided by lambda divided by c squared, which is h over lambda c. All right, so again, we're not going to have you be too responsible for these equations or have you use them in any real problems, but the point is de Broglie was able to derive an equation for the effective mass of a photon. It's h, which is Planck's constant, divided by its wavelength times the speed of light. So that means also, if this applies to photons, it also applies to matter. So photons have an effective mass, and then matter, which we know has mass, also has an effective wavelength. So if we rearrange the equation, lambda is equal to h divided by mass times velocity. So for a particle, for an atom or an electron or something like that, we replace c with whatever its velocity is. This is the speed of light. This is the velocity of whatever our particle is. And so for something moving through space, it has an effective wavelength, lambda equals h over mv, where v is the velocity of the particle and m is the mass. All right, so that's the de Broglie wavelength. And so in summary here, we have what's called a wave-particle duality. So matter and energy, or what we call electromagnetic radiation, both have dual particulate and wave properties. All right, so there are no longer two different distinctions between particles and waves. They're really one and the same thing, where waves have an effective mass, particles have an effective wavelength. So this idea came about, and we should realize though why was this not realized for so long? And it's because this really only applies for things that are very small, very small objects with very small mass, because h is such a small thing. So for example, if I were to throw a baseball to the back of the room, assuming I still have that level of athletic ability at my age, so if I were to do that, we could measure the wavelength, or we could think about the wavelength of the baseball. Now you're not going to see the baseball oscillating like you would a wave, and the reason is because if we calculate the de Broglie wavelength for something macroscopic like a baseball, h is 10 to the minus 34. The mass is on the order of, let's say, half a kilogram, maybe not even that much, but several hundred grams, and the velocity is whatever I can throw it at. I can't quite throw 100 miles an hour anymore, but maybe something close to that. So if we do the calculation for a baseball, the wavelength is extremely, extremely tiny compared to the size of the baseball. So you're never going to notice that the baseball has a wavelength associated with it. But for things that are really, really small, like electrons, if we were to calculate the de Broglie wavelength for an electron moving through space, we would calculate a wavelength that's on the order of the size of an atom. And so in reality, electrons do have wave-like behavior, which comes out of this equation. And then there are some experiments that were done that sort of prove that electrons exhibit wave-like behavior. So for things that are really tiny, like electrons, this wave behavior becomes evident in certain situations. All right, and the key experiment that was done to sort of demonstrate this is what's called diffraction. So diffraction is commonly observed with light. You may have done it yourself in a physics class where you take, let's say, a laser pointer and shine it through an array of slits, and you see the light scatter in all different directions in a regular pattern. So that's called diffraction. It's the scattering of light by a regular array of points or lines. All right, so that's what diffraction is, and there were some key experiments that were done which showed that electrons are diffracted by crystals. All right, we'll learn more about crystals later, but crystals are regular arrays of atoms where they have a very specific and well-defined space in between the atoms. And if you take a beam of electrons, which is conventionally thought of as a particle, and at the time nobody would believe that particles could diffract, but you take a beam of electrons, you put it on a crystal, it's going to diffract in all different directions. So the observation of diffraction of electrons was a very good demonstration that particles do in fact have wave-like properties. And the photoelectric effect that we just finished talking about is a good demonstration that waves also have particle-like behavior. So that's one of the ideas of modern physics that came about, is this wave-particle duality, where we can't just simply treat electrons as particles and photons as waves. They really all have one continuous form of matter that's both wave and particle in nature. All right, so that's kind of a very difficult concept. The math in this part of the course is not difficult, but the concepts are, and we're kind of jumping right into it with this atoms first approach. But we want to get to the idea eventually that electrons have wave behavior, and that's going to be an important point that comes back next week when we start talking about how electrons are arranged around the nucleus of an atom. But for now, let's just talk about some of the the simple equations that we've done and see some sample problems related to that. So the commonly available red laser pointers, which I guess mine's green, but we'll get to green one next. Those have a wavelength of 635 nanometers, and we want to know what is the energy of a 635 nanometer photon. All right, so again, the idea here is that when you have a beam of light, or in this case a very concentrated beam of light in a laser, it's going to be a huge collection of photons, but then each individual photon has a very well-defined energy that comes from this simple equation. So you will use these equations over and over again in the first chapter or two of this course. E is equal to h times the frequency, which is h times c divided by lambda. You can use either form of the equation depending on what's more convenient for you at the time. Here I'm giving you the wavelength, so that's going to be the form of the equation we'll likely use. So if we want the energy of the photon, we just have to plug the information into this equation. So the numerator here, h times c, is just two constants, and those constants are going to be on the periodic table that you use for the exams. So again, don't worry about memorizing them, although you'll use them so much you likely will, whether you want to or not. So we have 6.626 times 10 to the minus 34 joule seconds is h. The other constant is c, which as we've used already is 3 times 10 to the 8th. And then the denominator here, and again we have to be careful with units. We're using c in meters per second, so our wavelength has to be converted to meters. Alright, so this is the step that when you're in a hurry and when you're frazzled on an exam you might forget, so don't forget to do it. We have to always make sure the units match up. And you should get pretty good at converting nanometers into meters, because that's something else you'll have to do a lot early on. All right, so the wavelength in the correct unit is 6.35 times 10 to the minus 7. And so when we multiply this out, we get 3.13 times 10 to the minus 19 joules. All right, so as I alluded to, each little photon is a very tiny amount of energy, 10 to the minus 19 joules, which is, excruciating tiny. So photons are sort of like atoms. They're very, very, very tiny packets of energy, whereas a matter is, or an atom is a very, very, very tiny packet of matter, but they do exist, and that's what light is made up of, are these little photons that have very small energy, but when you have a huge collection of photons, then you can have, very large energy from that total collection of photons. All right, so that's the idea of how we calculate the energy for one photon, and now we can see how do we relate that to an entire beam of photons. So now we have, in this case, a green laser pointer, similar to the one that I'm using now, that has 520 nanometer wavelength, and we want to know how many photons are there in 2 joules. So let's say that I shine this, this would probably take a long time with this laser pointer because it's probably a milliwatt laser pointer. But anyway, if I shine this on the wall long enough to give the wall 2 joules of energy, how many photons hit the wall during that period of time? So how many photons do we need to produce 2 joules total of energy? All right, so again, we're going to find the energy for an individual photon using that equation. Hc over lambda. But again, remember, this number here tells us the energy of a single photon, which is going to be much smaller than 2 joules, I'd imagine. And then the wavelength here is 520, so we'll convert that to meters and get 5.20 times 10 to the minus 7 meters. All right, so same equation as last time, same exact operation as last time, but we're not done here. Remember that this 3.82 times 10 to the minus 19 joules is the energy of a single photon. And we want to know how many photons are in a beam of light that has a total energy of 2 joules, or that strikes the surface and gives, imparts a total of 2 joules of energy on that surface. So here we can just use a simple conversion factor. If this is the energy in 1 photon, how many photons are in 2 joules? So we have 2.00 joules of energy. We know that 1 photon has an energy of 3.82 times 10 to the minus 19 joules. So joules cancel, that converts joules into photons, and this is going to have a total of 5.23 times 10 to the 18th photons. So again, a very huge number. So to get a reasonable amount of energy, we would have 5.23 times 10 to the 8th photons. So to put this in more real terms, let's say you have a 60 watt light bulb. So a watt is 1 joule per second. So that means in 1 second, a 60 watt light bulb gives off 1 joule of energy, which means it's going to have something on the order of 10 to the 17th, 10 to the 18th photons in 1 second. So, a regular light bulb gives off a ton of photons. Each individual photon has a very tiny energy, and it's a huge collection of photons that gives you an appreciable amount of light. All right, so that's some examples of how we calculate the energy of light. Now what I want to do now, and we're running a little bit low on time, but what I want to do now is try the clickers out once. So if you have your clicker, get it out. And this one won't count for your grade, but we just want to make sure they work. So we'll do the question, see how it works, and then after class I'll put the score in a Blackboard. So you might want to check to make sure that if you answered the question that your score also gets linked to Blackboard. So you won't be able to see that right away, so if you look right afterwards you won't see it, but sometime right after class I'll do that, and later today you can check. So I'm going to open up this question in PowerPoint, because that's where I have the Alright, hopefully this shows up. Now this might screw up the screen recording, so it looks like let's do this. Alright, and then the question will be here. Okay. And I'll try to move this out of the way if I can. Oh, are you serious? Alright, I've discovered my first glitch. Here we go. We can move this good. Okay, so you can start answering the question now, and then I'll start a timer in a second to really get this going. So all you do is read the question. Yeah. Okay, channel. We'll get in there. I'm a noob. There we go. Channel 47. Now the other thing I should do, because I forgot to do this already, is let me start. In case you're using your phone, you also need a session ID. So what I need to do is start a session. Okay, so then that'll also show up when I go back. Alright, so channel is 47 if you have the regular clicker, and then if you're using your phone you will also need to duplicate this so it doesn't shows up. And then also you will need the session ID, which is there. Okay? So if you're using your phone to do this, that's the session ID I think you have to enter in some fashion to prove that you're here. Alright, so then I will start the polling and give you about 2 minutes to do this. And again, we're going to do this a few times before we start, making it count for real. So if you don't quite get it this time, don't panic. We'll figure out what's going on. Okay? And so you'll have about 100 minutes. Just give your best shot. And again, if you get the right answer or not, just try to enter an answer period so that we can record it and make sure that it's actually working properly for you. So if the time comes down to the end, just enter an answer of some sort, just guess, and that way we'll make sure that it's at least recording your responses, because this one's not going to count for a grade. All right, in case your eyes are looking down, you have 30 seconds to wrap up and just submit an answer. As I said, please put something in if you can, because I want to make sure it's working for everybody. All right, I'm going to pause it for just a second so more people can respond. We're up to almost 300, so I think that's the majority of you that are in here, probably. Okay, so it seems to have stopped, so I think everybody just about got it. All right, the polling is closed. So, all right, so we had about, this is all in the way now. Okay, so we had 44% select B, similar numbers selected A, and then C and D were the least popular answers, so let's see which one is correct. Okay, so we will exit out of here and go back to here. All right, so let's work through this one now, and then again after class, check to see if your answer got recorded to the blackboard. I'll make sure I can figure that out on my end too. All right, so what we have to do for this one, we're shining light on a surface, and this is related to photoelectric effect. If that light doesn't have a certain threshold frequency, which is related to what we call the work function or minimum energy, no electrons will come off. So we want to know if the work function of rhodium is 7.98 times 10 to the minus 19 joules, which of these wavelengths will eject an electron from rhodium? So the concept here is that the energy of the photon that strikes the surface has to be greater than the work function, which is sometimes abbreviated E0, related to the frequency, the threshold frequency in U0. So we want to know which of these wavelengths has photons that are greater in energy than this given work function here. So we set up this inequality. The energy of the photon, which is equal to hc over lambda, has to be greater than this value of E0 here that we're given in the problem. So we rearrange this and we see that the wavelength has to be smaller than hc over E0. So what we're going to do essentially is we're going to solve for a threshold wavelength, and then any wavelength that's smaller than that is going to have a high enough energy to eject an electron, because energy and wavelength are inversely related. All right, so when we put the numbers in here, 6.626 times 10 to the minus 34, 3 times 10 to the 8th for C, and then this E0 is what we call the work function. It's the minimum energy required to eject an electron. And so when we work this out, we get 2.49 times 10 to the minus 7 meters, which is 249 nanometers, which is the unit that I gave you in the problem. So that means the wavelength has to be smaller than 249 nanometers to eject an electron. So any of these that are smaller than 249 is going to work. So that's going to be A and C. So the correct answer, which I think was the least popular, is D. Okay, so that's okay. So many of you picked B because you solved for this value here and thought that the wavelength had to be bigger than that. But remember, the wavelength and energy are inverse. So if the energy needs to be larger than 7.98 times 10 to the minus 19, the wavelength needs to be smaller than 249 for that to be true. Okay, so we'll move on from that, and again, you can check Blackboard later to make sure that your score got recorded. I'll check it myself too and see how many of you got in. But we have a few more minutes left, so I don't want to stop just yet, because I won't get through everything today, but another concept we want to talk about which is related to the quantization of energy, or atomic line spectra. All right, so furthermore, investigating the relationship between light and matter. Please quiet down for just a second. All right, so if scientists also began studying energy of light that was given off by matter. So if you take an atom and you charge it up electrically or give it some sort of burst of energy, usually in the form of a spark, it will glow different colors. We've seen that with fireworks. Basically, when you heat up a substance to a certain temperature, it'll give off different colors when it comes back down in energy. So we have continuous spectrum as white light. So when you have a continuous spectrum like white light, the light that comes off of the sun or from a light bulb. Oh boy, did I freeze? My tablet's telling me that it's time to quit. Alright, I'll cover this next time because I don't want to wait 5 minutes for my tablet to come back to life.